In this lecture, we're going to go over the isentropic efficiency of compressors and pumps. If there's negligible heat transfer with the surroundings and no changes in kinetic or potential energy effects, the work input to a compressor or a pump is minus H2 minus H1. Just like for turbines, state 1 is fixed, and the work depends on the enthalpy at the exit. The magnitude of the work decreases as the enthalpy at state 2 decreases. So our minimum input corresponds to the smallest allowed value for the specific enthalpy at the compressor exit. So using a similar reasoning that we use for turbines, we can figure out the state for our exit. So our minimum work input is H2S minus H1. So in actual compression processes, H2 is greater than H2S, thus more work is required than the minimum. The difference is gauged by our isentropic efficiency, which is our isentropic work over our actual work, which is H2S minus H1 over H2 minus H1. It's very similar to the turbine one, except it is inverted, and isentropic pump efficiency is defined basically the same way. So we have an example. So for the compressor in this heat pump system, we want to determine the power and the isentropic efficiency. So let's fix our states. For state 1, it's minus 5 degrees Celsius and 3.5 bar. We're going to get H1 is equal to 249.75. And then for state 2, we have 14 bar and 75 degrees Celsius, and we're going to get H2 is 294.17. So our work is 0.07 kilograms per second times our change in enthalpy, which is minus 3.11 kilowatts. For the efficiency, we need state 2S. So S2S is equal to S1, which is 0.9572. So with S2S and P equals 14 bar, we're going to get H2S is equal to 285.58. So our efficiency for our compressor, which is H2S minus H1 for H2 minus H1, is 81%. Another example, we have saturated water vapor at 300 degrees Fahrenheit entering a compressor that operates at steady state with a mass flow rate of 5 pounds per second It's compressed adiabatically to 800 psi. If the power input is 2,150 horsepower, we want to determine the isentropic efficiency and the rate of entropy production. We can ignore kinetic and potential energy effects. So let's fix our states. So our compressor efficiency is our isentropic work over our actual work, just 5 pounds per second, times our change in enthalpy, divided by our given horsepower, which is 2545 horsepower. Horsepower, we get our efficiency to be 88.4%. For entropy production, we need state 2. We're going to do an energy balance. H2 is equal to our work plus H1, which is 2150 horsepower, 5 pounds per second times So we're going to look up P is equal to 800 psi and H is equal to 1484.2. We're going to get S2 is equal to 1.611. So our entropy produced is our 5 pounds per second. That's written really bad. Times our change in entropy. We produce 0.1804 horsepower per degrees Rankine in entropy production. In our next lecture, we are going to go over um, work and heat transfer for polytropic processes, and this will be our last lecture for chapter 6 and the course.